Today, in this video lecture, we will see one concept, average shear stress and numerical. Average shear stress. Average shear stress is the shear force per unit cross-sectional area, and this average shear stress is denoted as tau average is equal to shear force per unit cross-sectional area. Next example, draw shear stress distribution on a T section with wave 150 mm by 15 mm and flange 200 mm by 20 mm. The section is symmetric at vertical axis. The shear force applied is 110 kN. So for solving this numerical, problem statement is draw shear stress distribution, and they have given us in numerical shear force capital S is equal to 110 kN, and to finding shear stress distribution, so for solving this numerical, steps are position of neutral axis, to find position of neutral axis, second to find moment of inertia, then finding stresses at junction and stresses at neutral axis. So first write given data. Shear force capital S is equal to 110 kN, and to find shear stress distribution, position of neutral axis y bar. Let us consider this wave portion as 1 and this flange portion as 2. Y bar is equal to A1y1 plus A2y2 upon A1 plus A2. A1 is area for that wave portion, 150 multiplied by 15 mm. Two 2250 mm square. And y1 is equal to y1 is distance for that only wave portion, centroidal distance for that only wave portion from bottom fiber. That means 150 divided by 2, 75 mm. A2 is area for that flange portion, 200 multiplied by 20 mm. (4000 mm square), and y2 is equal to centroidal distance for that flange portion from bottom fiber. That means 150 plus 20 by 2. (160 mm). Y bar is equal to 2250 multiplied by 75 plus 4000 multiplied by 160 divided by 2250 plus 4000. 129.4 mm is position of neutral axis for that whole T section. Y bar is equal to 129.4 mm. This is first step. Second step is to find moment of inertia. Moment of inertia capital I is equal to Ixx1 for that wave portion neutral axis and Ixx2 for that flange portion neutral axis. Summation of both is this T section moment of inertia. Ix1 x1, this is for wave portion, and Ix2 x2 for flange portion. Here this is neutral axis for this wave portion Ix1 x1, and this is for flange portion x2 x2, and this whole T section neutral axis is y bar is equal to 129.4 mm. Here from bottom it is 129.4 mm. So for calculation of Ix1 x1 is parallel side this 15 mm as it is 15 into 150 cube divided by 12 plus area of that wave part 15 into 150 2250 and multiply by distance between this y bar 129.4 mm and y1 75 mm. That means this distance, this 129.4 neutral axis is above this x1 axis. Someone here neutral axis distance is 129.4 and this x1 distance is only that wave portion neutral axis, that means y1 is 75 mm. And distance between this is 129.4 minus 79 mm. 50.4 square plus now this Ix2 portion moment of inertia, for that x2 axis parallel side is 200 mm, 200 as it is, multiply by 20 cube divided by 12 plus area for that flange portion is 4000 and multiply by distance between this neutral axis and this x2 distance. This x2 distance is 160 mm from this bottom fiber, and this neutral axis is 129.4 mm. It means 160 minus 129.4 is 30.6. So 30.6 square. For solving this first curly bracket, 2250 multiplied by 50.4 square plus 15 into 150 cube divided by 12 is 9.93 into 10 raised to 6. It's 129.40 minus plus 4000 multiplied by 30.6 square plus 200 multiplied by 20 cube divided by 12 is 3.88 into 10 raised to 6. So this I moment of inertia is 9.93 plus 3.88 is 13.81 into 10 raised to 6 mm raised to 4. Here, see, distance between this neutral axis and this x1 axis is 129.4 minus 75 mm. This is 54.4. Here, not 0, is here 54.4. 54.4 multiplied by 2250 square multiplied by 2250 plus 15 into 150 cube divided by 12 is 10.87 into 10 raised to 6. And 10.87 plus 3.88 is 14.75 into 10 raised to 6 mm square. Now, next step is to finding shear stress at extreme top and bottom portion is 0, and next step is to solve shear stress at junction and shear stress at neutral axis. So third step, shear stress at extreme top and bottom is 0. And we have to find shear stress at junction. So for solving shear stress at junction, see, this is junction for that T section, and area about junction is this area above junction 200 multiplied by 20. So area above junction, capital A is equal to 200 multiplied by 20 is equal to 4000 mm square. And CGO of area above junction with respect to neutral axis is denoted as y is equal to, with respect to this neutral axis, CG of area above junction. So this is neutral axis. That means 170 minus 129.4 up to this distance from bottom is 170, and once this is up to this is 129.4. That means this distance is 170 minus 129.4 and minus this 20 by 2 is CGO of area above junction with respect to neutral axis. This total distance is 170. See, once again we have to find CGO of area above neutral axis. What is neutral axis? This portion is neutral axis, and neutral axis is at a distance of 129.4 from bottom fiber. And we have to calculate CG of area above junction with respect to this neutral axis. So for finding this, consider this total distance is 170 mm, and this distance is 170 minus 129.4. That means 170 minus 129.4 is 40.6. This distance is 40.6, and minus 20 by 2, deduct this distance 10 mm. This means CG area junction with respect to this much distance is 30.6. So right here, CG of area above junction with respect to neutral axis 170 minus 129.4, that means this 40.6, and minus 20 by 2. Is 30.6 mm. This y distance. Now width at junction B1 is equal to this 200 mm. This 200 mm is width at junction B1, denoted as B1. and B2 is wave portion thickness 15 mm. So using formula tau 1 is equal to SAY upon B1I. S is 110 kilonewton. That means 110 into 10 raised to 3 Newton multiplied by area for that flange portion is 200 multiplied by 20. That means 4000 mm square multiplied by centroidal distance for that flange portion with respect to neutral axis is 30.6 mm and divided by B1I. B1 for that wave flange portion at junction is, that means width of that flange is 200 mm and multiply by moment of inertia is 14.75 into 10 raised to 6. Tau 1 is equal to 110 multiplied by 10 raised to 3 multiplied by 4000 multiplied by 30.6 divided by 200 multiplied by 14.75 multiplied by 10 raised to 6 is 4.56 MPa. This S is in Newton. This area is in mm square. Is Y mm. B1 is also in mm. And this moment of inertia is in mm raised to 4. That means this mm get cancelled. This mm square and mm square get cancelled. That means remaining mm square, Newton per mm square is MPa. 4.56 MPa. This is stress at junction, first stress for that flange portion, and tau 2 is equal to this tau 1 multiplied by B1 upon B2. Tau 1 is 4.56 multiplied by B1 is 200 and divided by B2 is 15. Tau 2 is equal to 4.56 multiplied by 200 divided by 15 is 60.8 MPa. Now, next step is to calculate shear stress at neutral axis. For shear stress at neutral axis, area below neutral axis is this wave part thickness is 15 mm multiplied by neutral axis. That means area below neutral axis A is equal to this 15 is thickness of that wave portion and multiply by T section neutral axis from bottom fiber is 129.4. Area is equal to 15 multiplied by 129.4 is 1941 mm square. And CG of area below neutral axis is this neutral axis 129.4 divided by 2. 64.7 mm. and width at neutral axis is 15 mm, denoted as small b. Use similar formula, tau is equal to SA by y upon bi. S is 110 into 10 raised to 3 Newton, multiplied by area is 15 into 129.4, 1941 mm square, multiplied by y is this 129.4 divided by 2, 64.7, and divided by b is 15 mm, and multiplied by moment of inertia is 14.756 into 10 raised to 6. Calculate this stress. One 110 into 10 raised to 3 multiply by 1941 multiply by 64.7 divided by 15 multiplied by 14.756 multiplied by 10 raised to 6 is 62.41 MPa is shear stress at neutral axis. This tau is shear stress at neutral axis 62.41 MPa. Now see, this 62.41 MPa is shear stress at neutral axis, and this 4.56 is shear stress at junction, for, and this tau 1 is for above flange above that junction portion tau 1, and below that junction portion this tau 2 60.8 MPa comes. See shear stress distribution diagram. This is junction dotted line and this is neutral axis. This tau 1 is 4.56 MPa. So here 4.56, and just below that junction this tau 2 comes, this 60.8 MPa. And at neutral axis this 62.41. This is shear stress distribution diagram. So for solving this T-section shear stress distribution diagram, we first calculate position of neutral axis y bar, then moment of inertia, then shear stress at junction, then shear stress at neutral axis, and this is shear stress distribution diagram. Thank you very much.